6. Magnetic molasses. So an introduction. The purpose of this lab was to understand how we can induce a magnetic field through this experiment of dropping a magnet in an aluminum covered tube. We then also create a computational model in GlowScript to model the physical experiment we did in order to understand what is actually happening. So some important physics concepts to understand here is that we use the Biot-Savart law, Faraday's law, and Newton's second and third law in order to actually figure out how the magnetic field that was induced was affecting our magnet in the tube. So the physical experiment here, we have our system, which is our tube and magnet, and the surroundings is everything else. We first have to calculate some physical components of our system here, where the length of this tube is 46 centimeters, the aluminum thickness was 0.5, and then the inner radius of the tube is 1.25 centimeters. We also had to find the mass of our magnet. We then proceeded to take 5 trials of dropping our magnet down our aluminum tube in order to figure out how long it took to travel. So we took our 5 trials and we got that the average was around 1.09 seconds for this magnet to travel. So a big part of this lab was our computational model because we wanted to see whether the time that we got here was in fact accurate. So here in the computational models, we have our physical constants, which are obviously just the ones we've been using since day one. We have a graph that's being initialized, and then step 1 here is where we again input the physical constraints of our lab, such as I said, the length of the tube, the width, and the actual radius, which is the width of this foil plus the inner radius of the tube. Again, here, this is just more initialization given to us, and then we had to create the bar magnet, which I inputted the mass that we got, and this mu bag was something we had found in lab 3. Again, visualizing it, creating it, and then we have our initial conditions of the bar velocity as well as the time. We then had to input a very familiar equation here to find the dipole magnetic field of the magnet, which again, we got this from lab 3 as well. And this will help us later on. So here, we have a new part of this code where we have to calculate the change in flux over change in time, aka Faraday's law, in order to figure out the magnetic field and how it's affecting our magnet. So as you see here, there's a lot of numbers, but all we did was we took Faraday's law and we converted it into code. As you can see here, a lot of numbers, but what it essentially gets us is a change in flux over change in time. This is another simulation loop, which I will skip past here. So the force of the gravity we know because of Newton's law is negative mass times g because it's traveling downwards. And then we had to initialize mag F again, and we had to do the spur ring in tube. So this is the change in flux. We also had to find the ring current, which is obviously the change in flux divided by the ring. This is initialized, and then over here we had to use our dipole B we had to find the magnetic field of our B at ring for each ring that is around that aluminum tube. So this will be repeated as we go down. So calculating the magnetic force, all we had to do is use this code that we had calculated previously. We then know that F net is equal to the gravity, the force of gravity plus the force of magnetic field to get this. We then have the bar of velocity, which we can just add this in order to make sure it's updating as it travels down the tube, as well as position as it will also be updating as it travels down the tube. And so that is kind of the graph this is the math we did in order to eventually get this. So yeah, just all it shows you is how the velocity increases. It hits terminal velocity around here and then we catch it. So it's telling us that the time that it calculated was around 0.968 seconds, which, if you compare to our physical experiment, is pretty close. There is definitely a discrepancy there, but as I state here, some possible errors is that I may have not chosen the right parts of the video to calculate, so it's just human error where I may not have rightly calculated what portion the magnet was in the tube for. Some other possible error is maybe in lab 3 even my magnetic dipole moment that we had calculated may not have been accurate. So some assumptions we had is that there was no air resistance, and there was always the fact of Earth's magnetic field that we may or may not have perfectly negated. And yeah, so that is kind of the possible problems that could have occurred with this lab. So some what ifs. If the resistivity of our conductor was reduced close to 0, more freely through our aluminum tube, meaning that more magnetic field would be produced and the magnet would slow down more through our tube. However, if holes or slots were cut into our tube, this could affect our model because, again, that means that current is not going around in a circle anymore, in a ring around that magnet. It would not make a perfect loop, so that would mean less current, and that would mean that the magnet would not have as much magnetic field opposing it. Thank you.